So we have already started this chapter, crystallization, segregation and casting of metals, and so far we have gone through about what is nucleation. We have learned about homogeneous and heterogeneous nucleation, and we saw like how it happens and how the free energy term depends on both the volume free energy and surface free energy for nucleation. And so far, and here I want to mention that in the previous lecture I mentioned that the free energy decreases as the temperature increases, but there is a mistake here at this point. There is the graph, it was given as T2 is greater than T1, but actually T1 is greater than T2. And next, going forward, we have also learned about heterogeneous nucleation. So at this point we are ready to learn about what is growth. So growth is our second stage. First stage was nucleation and we are done with it. So here what happens, those nucleated portions will increase in its size. So during the process the volume will increase and some of the parent volume will disappear, and here you can see in the second picture. So these are the clusters. They become a nucleus when they cross the critical radius, and here you see the nucleus has grown. So this is the growth. Now let's see on what all the factors both crystallization and nucleation depends. So the kinetics of crystallization is given by JMAK equation, or so-called Arvami equation. Here you see equation number 13, which is known as Arvami equation, and it's very important for our subject. Here y is the fraction of transformation, k and n are time independent constants. Here k stands for both nucleation and growth term, and n exponent depends upon geometry of the transformation. Here by transformation I mean that from the stage of nucleation to growth. So when you plot this Arvami equation, you will get a characteristic curve which is like a S shape, and it's a very interesting fact that there is a lot of this kind of behavior you will see as well as in nature. For example, even in bacterial growth they show this kind of S character, but for us here, let's see what is happening here. You see that at the beginning the transformation didn't start. There was no transformation at the beginning from 0 to at this point. So this point is the phase where it's till the time where the system takes for nucleation, and after a certain time, from here the growth has started. That means nucleation is over and growth started. So when you see at 1, that means this whole system is fully transformed, and fully transformed. So from here we can see that after the nucleation the growth has it was a good increase in the growth, and at this point it reached quite it's increasing and it have reached a maximum. And here you see there is a region where you can see that the growth is in a steady condition. So this is how the kinetics of Arvami equation is explained, and you have to understand that it will take some time for nucleation before the growth starts, and then the growth starts slowly, and then it reaches the highest position, and at some position the growth will be in a steady state. So let's see how it will look if I plot the nucleation rate, growth rate, and overall transformation, how the kinetics will look like. Here the blue line is your nucleation rate, which is a light blue, and this red one is your growth rate, and this dark blue is your overall transformation rate. Here you see that the nucleation has started below some temperature at this position, which means that some undercooling is required. Some undercooling is required for the nucleation to begin. So by undercooling, I mean that it's cooling below the freezing point. Below the freezing temperature is called undercooling. So here, to initiate nucleation, some undercooling is required, and which is the driving force for nucleation. So here you see the nucleation will here the nucleation has started and it has reached a maximum, and the nucleation rate then slowly start to decrease, and then slowly here it slowly start to decrease. So the reason behind it for for nucleation to take place, some diffusion of atom is required. So when the temperature goes down, there will be very few diffusion, and hence the nucleation rate will decrease. The same thing will happen with growth. So with growth, the thing with growth is that once after nucleation, growth will start, and just like the nucleation rate, it will also increase, and after a certain position it will decrease. The reason is same, which is the decrease of due to the slow diffusion. So as I told, with temperature diffusion will decrease, and hence growth rate will also decrease. So this overall transformation rate is the combination of nucleation rate and growth rate. So here you can see it also follows the same kind of trend, and the reason of decrease of the transformation rate is also same as the same for the growth rate and nucleation rate. So now we are at a position when we understand that when we during the phase transformation, or when we try to cool a liquid metal, the liquid phase of metal nucleus. So first we see the liquid phase, where the small nuclei will appear after a certain temperature or after certain undercooling, and then you see this nuclei will grow, and the growth will take place, and then finally you get the grains of solid material here in the third picture. So here you see a completely solidified grains, and there are grain boundaries, and this is how the grains are formed. So now we are at a stage we understood how the grains formed and during solidification. So in the next phase we will talk about crystallization. We will talk about different kinds of grains and how they are forming, and what are the driving forces for creation of these grains. So here you see in the picture that there are some grains are formed. So this one at this boundary is called equiaxed grain, and here at the center also we call it as equiaxed grain, and those the longitudinal grains we call it as columnar grain. So this whole thing is considered to be a vessel. It's a vessel or a mold. Suppose it's a mold where you pour the liquid metal. So when you will pour the liquid metal on a mold, the this is this is considered this as the boundary or the wall of the mold. This is the wall of the mold. So in heterogeneous nucleation, we have learned that at the surfaces or at the walls of the wall of this vessel, it will be always heterogeneous nucleation taking place. So here also some heterogeneous nucleation has took place, and this heterogeneous nucleation has given this small equiaxed particle. So, or the equiaxed particle or the equiaxed grain better. So, and one more thing I want to tell you that the meaning of equiaxed grain is that this equiaxed grain have approximately equal dimensions in all directions. So they are called as equiaxed grain. And this process of pouring a liquid metal into a mold to give an impression is called casting of metals. So when you pour liquid metal in a mold to give it a 3D image or 3D impression or shape, this process is the casting of metal. So I explained you up to here that we got some equiaxed grains at this position. So let's see what happens next and how it's happening here. As I told, the heterogeneous nucleation will always take place at the boundary or the wall of the container. But what it happens after a certain layer, there will be no equiaxed grain. At this position, the heterogeneous nucleation has stopped and homogeneous nucleation has started playing the role. If you remember from the last lecture, I told that homogeneous nucleation always takes place at the core of the liquid. So here, this is from the core of the liquid, the homogeneous nucleation is taking place and giving some elongated or it's better term, elongated grains, which is known as columnar grain, and the orientation of these grains will be following from the surface of the container to the center of the container. And there is a very valid reason why they are following this direction or the trend, is that it is because of the temperature gradient. So keep in mind when you pour the liquid metal into the vessel, the surface of the vessel will have the lowest temperature, and the center the temperature will be maximum. So there will be a temperature gradient from the center towards the surface of the vessel. And this columnar grain, they always grow in a direction opposite to the temperature gradient. So here the temperature gradient is from the center to the surface, and the columnar grains are forming from the surface to the center. But there is a problem. So after it grows to a certain, this columnar grain grows to a certain position, this nuclei will resist the growth of the neighboring nuclei, and hence at the center again equiaxed grains will be forming. So here you see it has the whole solidification process started with equiaxed grain, then columnar grain, and again equiaxed grain. So let's see what happens next. So here I have put another diagram that explains the temperature gradient in a better way. Here T2 red zone is the fully liquid zone, and this is the boundary of the vessel. T1 is the zone where the solidification has started, first initiated. At this position solidification has initiated, and the temperature gradient is from T2 to T1, as I said, from the core of the vessel towards the surface of the vessel. So here you see the columnar grains are growing in a direction opposite to the temperature gradient. So this is the thing. So next is the dendrites. We have broadly discussed about dendrites in my previous lecture for the chapter number 3, and here they comes to play once again. So what will happen when this columnar grain will develop some arms, and these columnar grains are approaching towards the center of the casting, and they develop some arms. We call it as dendrites or dendritic grain. And on the other hand, as I told in the previous for my lecture for the chapter number 3, that there is a high probability of forming the dendrites at the inside the liquid metal. So here you see at the center these are equiaxed grains. That means they are equal in size and shape, but they have some spikes or arms, so they are equiaxed dendrites or dendritic grains. So if you see this picture, at this position the solidification has started, and these are non-dendritic equiaxed grain. Then the solidification proceed. Here these are columnar dendrites, and at the center these are equiaxed grain, but they are dendrites. They have some arms. So at this position you see that you see that there is a mold. There is a mold here, the gray color. This is the mold or the cast, and liquid or the melt is poured here. The liquid metal is poured here. So at this position you see this equiaxed dendrites, and these are at the boundary non-equiaxed dendrites. These are the columnar grain, and this is the directional solidification, means they are growing towards the center of the mold from the surface, and this is the melt flow. So here you see at the position when they're at the center where we have the melt, the liquid metal. Here the nucleation has started, and you can see some equiaxed dendrites. So these are the equiaxed dendrites. So this is a schematic diagram, but in practical, in when you actually solidify a metal, it looks like this, the second picture, which is in black and white. So actually in practice they looks like this. So now again, like depending on the size of grains, there are two types of grain: coarse grain and fine grain. So here you see that coarse grains are uniform, and they are bigger in size, whereas fine grains are comparatively smaller in size, and they have different structures. But here is interesting point that there are some criteria under which this coarse grain and fine grains forms. So the criteria for formation of fine grain is that when the rate of crystallization and the ability to crystallize is high, fine grains will form. On the other hand, if the rate of crystallization and ability to crystallize is small, coarse grain will form. But I want to tell you, it's always preferable for steel or most of the metals that it should have fine grain structure, because fine grain structure gives better strength. So next is the structure of cast alloys. So we have already learned, this is not much new to us. We have seen that three kinds of grains that has formed. So in picture 1 you see the columnar dendritic grains. These are the columnar dendritic grains, and they are approaching towards the liquid phase. Next is equiaxed dendrites. This equiaxed dendrites has started forming exactly on the liquid phase at the center of the mold. And third one is that non-equiaxed, non-dendritic grains. These are, you can see, they are just next to the solid solid phase or at the surface of the container. So the next topic, which is again very important for you to know, which is the how the trend follows for the crystallization of pure metal. Here you see the graph. It is a temperature versus time graph. So initially when you pour the liquid melt, it's here you see when you pour the liquid melt, it slowly cools down, and which can be seen in the y-axis here, and where the temperature is plotted on the x-axis. But the thing is that the crystallization should be initiated or supposed to start at the freezing point. But to initiate the crystallization, some undercooling is required. As I told, undercooling means cooling down the sample below the freezing point. So this will provide the activation energy or the driving force for nucleation, and then at the freezing point the crystallization will start. And so both freezing and crystallization will take place at the freezing point. So constant temperature crystallization takes place, and once the crystallization is over, here the crystallization is over, and the system or the liquid is crystallized. And here you can see that that from this point, at this point we call it that casting is fully solidified, and this last portion of the graph, the solid is cooling. Hence the solidification of pure metals goes through the path. It slowly cools down, some undercooling is required, then it gets back to the freezing point, and at the constant temperature crystallization will start and end at the same time, and then the solidification will take place. So we have learned so far that how the crystals will form, what all the different kinds of grains will form, and how it will solidify. So here at this position, before I discuss segregation, I want to tell you that segregation is something that comes to play because of the less soluble solutes in the melt. So if I take the example of steel, that is the iron carbon system, we know the base material is the iron, and carbon is added to it to get steel, and so this is the thing, when when you try to add something to the base material, the lattice structure of, there will be a distortion in the lattice structure actually. and the lattice will always try to push out the other material. So when there will be distortion in the lattice, the free energy will increase. Hence, as we know, all the systems try to get a lower free energy. Hence, the base material will try to push any other material, and it can happen both in liquid and solid phase. So, so this is the thing of the this is the thing that this phenomena when the liquid or the base material try to push out any of the other material or any of the maybe it may be a substitutional atom or interstitial. So I was discussing that during segregation, this base material always try to push out this substitutional or interstitial atoms, which try to form a distortion in the lattice because of their presence. So it's by pushing this substitutional atoms, the base material always try to create an interstitial free or defect free lattice. But the lattice cannot push out all the solute elements in the liquid at a certain concentration of the both solute and solution. This process of rejection will stop. So this is the process of this is what we call as segregation. Now segregation is of again two types. One is the macro segregation, and other is the micro segregation. So in macro segregation, it occurs during the solidification, and the concentration of the impurities in the center of the casting will be higher as the solidified particle will push the impurities in the liquid phase. As I just told, they try to push, and in the macro scale what it happens is that this solidified particles or those portion, I will tell you, like here near the surface of the mold, this here is the portion where the solidification is initiated, and from this part the impurities will be pushed towards the center, towards the liquid, and hence due to the reason of macro segregation at the center, this liquid is always highly alloyed or overly alloyed, and this is the process of macro segregation. Now let's see what will happen in the micro scale. So in the micro scale there will be, I mean, as I already explained you, that the base material will not be able to reject all the impurities or the solute which is mixed to the base material, but some of them will be always present in the mixture or in the liquid, in the solute. So here what will happen, the distribution, now whatever amount of solute is left within the system, it will be distributed locally, or and we call it as micro segregation. In this case, the concentration distribution of impurities will take place at dendritic branches. So it's like when it will be pushed from the center towards the arms of the dendrites, and it's this micro segregation. A lot of time it happens at the grain boundaries, which is a very preferable position for micro segregation. So in this lecture I'm closing for this portion, and in this portion I have covered about this crystallization and the kinetics of nucleation and growth and segregation. So thank you for your attention.